Today we are going to see solution or one solution of a linear second order homogeneous ordinary differential equation. We know a linear second order homogeneous ODE that can be written in this form: d square y by dx square p of x dy by dx plus q of x y that is equal to 0. And in this section we see that a solution of this equation can be obtained in the form of an infinite series. Okay, a solution. Actually, a second order homogeneous differential equation like this has two independent solutions. If we have one solution with us, we can develop a second independent solution. Anyway, a second order homogeneous linear differential equation has two independent solutions, and we can prove that no third independent solution exists. So there are only two independent solutions. Okay, so y1 of x, that is one solution. It may be in the form of a series. We are going to see the method to obtain one series solution, and we can obtain second solution. We will later on see how we can obtain the second independent solution, and we can prove that no third independent solution exists. So if there are two solutions, y1 of x and y2 of x, the most general solution that can be written as c1 y equal to c1 y1 of x, c2 y2 of x. Okay, so this is the most general solution. Okay, and we see a method. This is called the Frobenuis method for finding series solution. One solution, a series solution of a linear second order differential equation. Okay, the method actually involves a series expansion. Frobenuis method that involves a series expansion, and this series expansion will always work provided that the point of expansion is no worse than a regular singular point. If the point of expansion is no worse than a regular singular point. Last class we were discussing about ordinary point, singular point, regular singular point, irregular singular point of a differential equation. In the series expansion, we use a point for the expansion, and that point for this method to work has to be a regular point, or if it is a singular point, it has to be a regular singular point. So ordinary point, expansion will work. Singular point, the expansion will work provided if it is a regular singular point. For irregular singular point, the series expansion will not work. Okay, so this is what is said here. And in physics, for the differential equations that we use in physics, this condition is almost always satisfied. we can always find points which are either ordinary point or a regular singular point for obtaining series solution. Okay. Now, how do we use, or what is the Frobenuis method? Suppose we have x0, which is, as I said earlier, an ordinary point or a regular singular point. Then the solution consists, the solution is this: y of x equal to y of x, that is the solution, that is equal to sigma lambda equal to 0 to infinity a lambda x minus x0 k plus lambda. Okay, so we have an infinite series here. Lambda takes values from 0 to infinity. The condition is a0 not equal to 0. So this is how we obtain the series solution. The solution has this form. Okay. To illustrate the method, we use the linear harmonic oscillator equation, which is this: d square y by dx square plus omega square y equal to 0. d square y by dx square plus omega square y equal to 0. And we are trying to obtain a series solution of this linear harmonic oscillator equation, which is a second order differential equation. And we already know there are two solutions: y1 equal to sine omega x and y2 equal to cos omega x. This equation is very much familiar to us. Okay, and we already know the solutions of these equations are y1 is sine omega x, y2 equal to cos omega x. Okay, and the general equation or general solution is this: y equal to c1 y1 plus c2 y2. Now, to obtain the solution of this equation by using this method, what we do is we expand about x0. Okay, we are taking the point x equal to 0 as the point of expansion, which is simply an ordinary point. This is not a singular point of the differential equation. So we use x0 equal to 0. So this is the point of expansion. So y of x will be this: sigma lambda equal to 0 to infinity a lambda x raised to k plus lambda, where a naught is not equal to 0. Now we differentiate this equation twice. So dy by dx is this: a lambda. As we differentiate this, we will get dy by dx as k plus lambda x raised to k plus lambda minus 1. And d square y by dx square, that is given by a lambda k plus lambda minus 1, k plus lambda minus 2. So this is d square y by dx square, this is dy by dx. Now we substitute this in equation 1. Substitute this in this equation, the equation 1. dy by dx is not there in this. We need d square y by dx square. That we substitute. So as we substitute, you will get this. When we substitute for d square y by dx square, you get this. And when you substitute for dy by dx, you get this. Okay. So we have this important equation with us. Here, what we are going to do now is, as we expand, we put lambda equal to 0 first, then lambda equal to 1, then lambda equal to 2. As we put lambda equal to 0, we get the lowest power of x, which is x to the power k minus 2. Okay, x to the power k minus 2, when you put lambda equal to 0. Here you will be getting x raised to k when you put lambda equal to 0. So lowest power of x for lambda equal to 0. And we take the coefficient. The lowest power of x is x to the power k minus 2. We take its coefficient. And what is the coefficient? When you put lambda equal to 0, here you will have a0, here you will have k, here you will have k minus 1. So this is the coefficient of x to the power k minus 2. Okay, so that is written here. The coefficient is a0 k into k minus 1, and this must be 0. Why? Because see, on the right hand side of the equation, that is 0. So the coefficient has to be 0. Okay, so we have this k into k minus 1 equal to 0. And this is called the indicel equation. Okay, we call this as the indicel equation. So we have got the indicel equation, k into k minus 1 equal to 0. What that means is k is 0, either k is 0 or k equal to 1. The solution of the indicel equation is k equal to 0 or k equal to 1. Okay, so how do we get the indicel equation? By comparing the coefficient of the lowest power of x. The lowest power of x, we get the indicel equation. Next step, we compare the coefficient of x to the power k minus 1 by putting lambda equal to 1. So here we have this equation. Here we put lambda equal to 1. So we have a1 here, k plus 1 here, k here, and here you will have lambda equal to 1. So you have x to the power k minus 1. Okay. So this is the coefficient a1 from here, then k plus 1 here, and k here. And the coefficient is a1 k minus 1 into k. So we have the coefficient of x to the power k minus 1 as a1 k plus 1 into k, that is equal to 0. And we know if k is 1, suppose we know k can take value 0 and k equal to 1. When k is 1, this will be 2 and this will be 1, and a1 has to be 0. a1 must be 0. Okay. And if k is 0, a1 is arbitrary. Okay, a1 is arbitrary. If k is 0, a1 is arbitrary. Then the coefficient of x raised to k plus g we are taking. Okay, so from the first part you got the indicel equation, and the roots of the indicel equation are k equal to 0 and k equal to 1. And then taking the coefficient of x to the power k minus 1, you got what? The value of a1. a1 is either 0 or arbitrary. Okay. Now we are taking the coefficient of x to the power k plus j. Okay, x to the power k plus j. So that we can obtain by putting lambda equal to j plus 2 in the first summation and lambda equal to j in the second summation. So here you take, here if lambda is j plus 2 here and lambda equal to j here, we get the coefficient of x to the power k plus j. Okay, I want the coefficient of x to the power k plus j. So here I am putting this as j. Here lambda is put as j. Okay, so when lambda minus 2 is j, lambda will be equal to j plus 2. Okay, so lambda equal to j plus 2. So I will be getting what? This. From the first summation, I will get a j plus 2, k plus j plus 2 into k plus j plus 1. From the second summation, we will have omega square aj, that is equal to 0, or aj plus 2, that is equal to minus omega square aj by k plus j plus 2 into k plus j plus 1. So this is a plus j, a j plus 2. Okay, minus omega square aj over k plus j plus 2 into k plus j plus 1. So what we obtain here is the recurrence relation. Okay, this is the recurrence relation. Why we say this is a recurrence relation? If we know aj, from aj I can obtain aj plus 2. Okay. So from a given aj, we may compute aj plus 2, aj plus 4, aj plus 6, like that. Okay. So this is called a recurrence relation. So by taking the coefficient of x to the power k plus j, I am getting the recurrence relation. I hope you remember the steps through which we have passed now. Now we know a1 is arbitrary if k is 0. In the second step we had said a1 is arbitrary if k is 0 and it is necessarily 0 if k equal to 1. Now let us set it as equal to 0. So we are taking a1 as 0. Okay, because a1 is 0 when k is 1. For k equal to 0, we don't know the value of a1. It is arbitrary. So we are choosing a1 as 0. So a1 is 0. Okay. Now by the recurrence relation, if a1 is 0, a3, a5, a7, all of them will be 0. Because here for j equal to 1, I will get a3. For j equal to 2, I will get, sorry, for j equal to 3, for j equal to 1, I will get a3. So a3 is minus omega square a1. Since a1 is 0, a3 is 0. a3 0 means if I put j equal to 3 here, okay, j equal to 3 here, I will be getting 5. Since a3 is 0, a5 is 0. So all these odd coefficients will be zeros. Okay, that's what we have written here. a3 equal to a5 equal to a7, all of them equal to 0. Now we are going to find the solution. We first try the solution for k equal to 0. Okay, we try the solution. Then the recurrence relation becomes aj plus 2 equal to minus aj omega square j plus 2 omega square by j plus 2 into j plus 1. We put k equal to 0 in the recurrence relation. Okay, so using this I can find a2. How do I get a2? If I put j equal to 0, If I put j equal to 0, I can get a2 here. So a2 is this minus a0, this minus omega square by 2 factorial a0. a4 is, by putting j equal to 2, I can get a4. a4 is this. Okay. And a6 is this, or we can write this general relation. a2n is minus 1 to the power n, omega to the power 2n factorial a0. So this is a2n. And by substituting in the solution that we assumed a solution of this form. Okay, so here we put k equal to 0. So what we have is x to the power lambda here, k is 0, so x to the power lambda here. And as we expand, we will have the first one a0, then a1, then a3, because we know, a0, then a2, then a4, because we know a1, a3, a5, all of them are 0. Okay, so we have this solution, a0, this into this. Okay, such a series solution we obtain. All these a3, a5, a7, that are all 0. And this is actually cos omega x. So this is y of x is a0 cos omega x. Okay, now if we choose the initial equation root k equal to 1. The previous one we took k equal to 0 and we got a solution. What is it? a0 cos omega x. Now we take k equal to 1 and we have aj plus 2 equal to this. Okay, and here we put j equal to 0, 2, 4, etc. We put and we get a2 as equal to this. Okay, a4 as equal to this, a6 and a2n as equal to minus 1 to the power n, omega to the power 2n factorial a0. Okay, and as we substitute in the series by taking k equal to 1. Okay, so when you expand the series, here you have to take k as equal to 1. This is the series. So here you have to take k as equal to 1. Okay. So a0 x, that will be the first term. Then a2 x cube, that will be the second term. It goes on like that. Okay. And you will be getting this y of x and k equal to 1 as this. And if I take an omega or bring an omega here, I want to introduce an omega here by introducing omega in the denominator. So I will have sine omega x. So a0 by omega sine omega x. So we have got the two solutions, two series solutions of the linear harmonic oscillator equation by using the Frobenuis method. So we have illustrated the Frobenuis method by using linear harmonic oscillator, and we follow the same steps, same method for obtaining the solution of Bessel equation and then the Legendre equation.